In the last video and in the last unit, we discussed samples versus populations and the idea that we collect data from a sample and then hope to generalize our findings from the sample to the population as a whole. What happens very often for research is that the researcher, instead of just looking at one sample, will want to compare two different samples. And generally, the research hypothesis is that these two samples are significantly different from one another. These two groups of people come from different populations, distinct and independent populations. And so these two samples represent, or these two groups represent samples drawn from different populations. The null hypothesis, on the other hand, would state that these two groups or these two samples come from the same population and that any differences that we observe in the sample means is purely due to chance or random sampling error. So that's a really important point because we wouldn't expect two different samples, even if they're drawn from the exact same population, we wouldn't expect those sample means to be exactly identical. And we talked about that last time, this idea of the central limit theorem. And if we draw multiple random samples from the same population, even if we know that we're drawing from the same population, you can see here that our sample means are somewhat different. But we recognize that this is due simply to random sampling error. So a real question when we're comparing two different samples or two different groups is, are the differences that we observe in, let's say, the mean for these two different groups, does that represent true population differences? Or is that difference simply due to random error? And so a lot of times in research, we may want to compare two different known groups on some dependent variable of interest. So maybe I want to compare Democrats to Republicans. Maybe I want to compare seniors to freshmen on some variable of interest. Or maybe, and you'll see this a lot, I want to compare a treatment group to a control group. And so you can see here, I pulled these from your slides, that we have method A and method B, right? Where you could switch this out for experimental group or control group, maybe. You see a series of scores for participants in each group. So each group here has 5 participants, and we have scores for our dependent variable. And you see that our means are different. Right? So the mean of method B is 77, the mean for method A is 82, but the idea is that we can't simply say, well, we see a mean difference between the two groups, so our research hypothesis is supported. There is a difference between the two groups, because that's not exactly what we're asking. We're not asking, are there mean differences between two groups, but instead, are there differences at the population level? Are these two groups coming from two distinct populations? And so we have to look at and see whether these mean differences are between the groups are greater than what we would expect due to random sampling error. And so what factors into random sampling error is the range or variance of the scores within the particular population. What we have access to is the range or variance of scores within each group. And so you can see in this set here on your left that there's not a wide range of scores. They're very closely clustered together. So here our range is from 80 to 83. And for method B, Our range is from 76 to 78. They're really close together. So when we see a range of scores within a group of only, a couple of points, and then we see a difference between the groups of 5 points, right? That's much stronger evidence of a true difference between these group means compared to this table over here on the right. So here, my range of scores within method A and then within method B are a lot greater. So you can even see if you compare some of these scores, the overall group mean for method A is higher than for method B. But if you look at the individual scores, there are several instances in which people over here in method B are scoring higher, and in fact much higher, than people over here in method A. And so in method A, our range is from 63 to 98. So we have a range of 35 within this group, right? Versus between groups, we still have that same mean group difference of 5 points. So they're ranging a lot more within a group than they are between groups. And so that's really what we're going to get at with our comparison of group means and the t-test. So let's look at conducting a t-test. And so I have a brief scenario here that is very similar to the one that you have in your quiz. And so in this particular study, a researcher administers a stats exam to 90 participants. And this researcher wants to compare two groups. So in our first group, we have 40 participants who are given caffeine. In our second group, we have 50 participants who are given water. The researcher measures the number of calculation errors made by each participant. The question asks, using the data provided, test the difference between the means. And so here we have some data for our caffeine group. Again, this is 40 participants, so we have an N of 40. They have a mean number of calculation errors here of 6.2 for this particular group, and a standard deviation of 1.4. If we compare that to the water group, we have 50 participants, so an N of 50. Our mean is 8.4 calculation errors. We have a standard deviation of 1.2. And so the first thing that we'll want to think about is what is our research and our null hypothesis. So our research hypothesis would be that there is a significant difference between the caffeine group and the water group on the number of calculation errors made on the stats exam. Our null hypothesis is simply that there is no significant difference in calculation errors between the caffeine group and the water group. And so we want to conduct a t-test to test our null hypothesis. Are there significant mean differences between the groups or not? So the first thing that we'll want to do is to calculate the difference between our two groups. And so we can take our water group of 8.4 minus the mean for our caffeine group of 6.2. And so that will give us a mean difference of 2.2. The next thing that I like to do is to calculate the degrees of freedom. So our degrees of freedom has a pretty simple formula. So we want to take the N for each group, 40 plus 50 will give us 90, and we want to subtract 2. So we're subtracting from the total sample size of 90 participants. We're subtracting the number of groups. So in this case, we have 2 groups. So 90 minus 2 would give us a degrees of freedom of 88. Now we have several pieces very quickly several pieces of information that are very useful for conducting our t-test. So this mean difference of 2.2 would be the numerator for our t-test. So if we have t, that would be what would go in the numerator portion of our equation. We'll use this 88 degrees of freedom at several points, but we need to, in order to calculate our obtained t value, we need to determine what is our denominator. And I have pulled in this formula from your slide so that we have it here. And as you can see, this is a little intimidating. We'll walk through it just so that you can see that it's not nearly as complex as it looks, but I want you to understand this conceptually. So the reason that we have this kind of complex formula for our denominator is that our denominator is taking into account the variance within each group, just as we talked about a moment ago. So we have a ratio of between group differences, our numerator, to within group variance as our denominator. So we're looking to see, does the between group differences far outweigh the variance within the groups? Now, because we have two separate groups, we have two separate standard deviations. And so we need to pull these together. We need to pull the variance of the two groups. And what we're doing here, why this equation looks so complex, is because we're weighting each of these standard deviations, or really because we're squaring them here, each of these variances for the groups, we're weighting each of these by their group size, because you can see here that our group sizes are not the same. And we learned in a previous chapter that the larger the sample size, the more precise the estimates, the better estimates we're getting for estimates of population parameters or population values. And so this equation here is taking that into account. It's saying we need to give more weight to estimates of variance that come from the larger groups. Now, as long as you understand that conceptually, I tend to think that working through this particular equation is more tedious than anything. There's kind of an old guard within academia that very strongly argues for doing a lot of calculations by hand. And I think maybe part of that comes from the fact that they were forced to do that. And so then we need to force everyone to do that. And I don't necessarily agree. Many calculations, I do feel that it adds to your understanding of conceptually what is it that we're testing. But with specifically this equation here, I'm not sure that we're getting added value by you walking through and doing these hand calculations. So I'm going to walk you through one example just so that you kind of get an idea of what we're doing. But for your homework, and I will also add this to your quiz, I will tell you, use this number as the denominator. And so you'll calculate out the mean difference to get your numerator, and I will give you this value here for your denominator. And so all you have to do is this very simple division. All right, so let's walk through this. I'm calling it here the error. You could call it the pooled variance estimate. Either way, it's our denominator for obtaining our t value here. So you'll see that you have these items within the equation that are squared. So what we're doing is we're taking the standard deviation for each group and squaring it. So I'm going to get that value first, just to help us along the way. So my 1.4 squared would give me 1.96. My 1.2 squared would give me 1.44. Now let's kind of step through this. This N1 refers to the sample size of our first group. So that would be 40, and we'll multiply that by our 1.96, and then we would add our sample size for the second group of 50 multiplied by our standard deviation squared, which was 1.44. Then we would divide all of that by, if you'll notice, this N1 plus N2 minus 2, that's the same equation that we used for our degrees of freedom. So we know that that would be divided by 88. So let's get that worked out first. Okay, so we have 40 times 1.96 plus 50 times 1.44. We want to divide all of that by 88, and so we get 1.71. And then we would multiply that by this equation here. So you have N1 plus N2. So 40 plus 50 divided by 40 times 50. 40 plus 50, let's go ahead and we know that that's 90, divided by 40 times 50 would be 2,000. So I'm going to go ahead and divide that out and multiply it by 1.71. So 90 divided by 2,000 is 0.045. Multiply that by 1.71 would give us 0.08. And then I want to take the square root of that. So don't forget about the square root radical here. So square root of 0.08 would give us approximately 0.28. So my denominator here would be 0.28. So if I divide out this, my obtained t value would be 2.2 divided by 0.28 to give us 7.86. Now, we've obtained our t value. We still have to use this obtained t value to test our hypothesis. And so what we're going to do, beginning with this chapter and then kind of carrying throughout the chapters, it'll follow the same basic formula. You'll generate a research hypothesis based on the scenario, a null hypothesis. You'll obtain a statistic. You'll calculate out a value. You'll compare that calculated or obtained value to a critical value that you get from the table. And so we've used the t-table in your last unit. We'll use this t-table again to get our t critical value. So anytime you see a question that asks you for your t critical value, that's when you'll turn to this table. And so you should be familiar with this. You use here your degrees of freedom column. Your degrees of freedom column, and look for the degrees of freedom. We determined that our degrees of freedom are 88. That's not listed. The next closest that is lower is 60. So we're going to use this row, and we want to test it at the 0.05 alpha level. And so it's this column here that we want to use. And so we go across from 60 to our 0.05 column, and we see that our t critical value is 2.00. And so we're going to compare our obtained t-value to this critical value of t. And what we're really looking for is to see whether the one that we've calculated, right, the one that we have obtained through our calculations, is that t-value greater than the t critical value. And if it is, then we reject the null hypothesis and we support our research hypothesis. We state that there is a significant difference between the two groups. And so we can go back to our example. Say their t critical value equals 2.00. We're comparing that to our t obtained of 7.86. And so our obtained t is larger than our critical t. And so our decision would be to reject the null that states that these two groups come from the same population, have the same mean. And instead, we're saying that there are significant differences in calculation errors between our groups, between the caffeine and water groups.